We're going to start something totally different today. So the next section of the class you could think of as being called the road to the zeta function. So this is sort of unit 2. And sort of my plan for talking about the zeta function. My plan for talking about the zeta function is going to be that I want to start talking about interpolation problems, which I'm going to describe. I'm not just going to drop the word interpolation on you without telling you what that means. I promise. So we'll talk about interpolation, and then we'll talk about the gamma function. And our discussion of the gamma function should motivate our a discussion of what's called analytic continuation, which we've already seen a little bit in the last quarter. So you can think about analytic continuation as being the study of how to extend the domain of an analytic function. And then from there, we can talk about the zeta function. And then for the two of you in the room who haven't seen it, we'll have a brief discussion maybe about, once we have the zeta function, maybe we'll talk about 1 plus 2 plus 3 is equal to minus 1/12. Like, in what sense that could possibly have meaning. If you have not stumbled across the entire industry of YouTube videos around this idea, then it's out there. Okay, so the first thing I want to talk about is, what is interpolation? You've been doing this since you learned what parabolas were. What are you trying to read? Continuation. That's okay. This is sort of my plan for what we're doing here. Okay, so an interpolation problem means this. You are given what is sometimes called initial data. So, I don't know, maybe we'll call it lambda 1 up to lambda n, which is inputs. And you're given target data. So we'll write it z1 through zn. And the idea of an interpolation question is find a, and we'll put a box right here, function f, so that f of lambda I is equal to zi, where I equals 1 to n. Okay, so that's sort of the textual definition of it. The idea is what goes inside this box is however nice you need your function to be. What could be inside this box could be the word continuous, could be analytic, could be bounded, could be polynomial. So there's a lot of choices that you can impose on how you want this function to behave. I'm going to draw a picture of what's going on here in a second. The idea is I want something where I tell you what the inputs are and I tell you what the outputs are and you find me a function that does it. Normally at a bare minimum we want continuous in here. So like what could go inside this box? Some different combinations of conditions we might ask for include things like continuous or differentiable, bounded, or analytic, or polynomial is the classic one, which is what I'm going to start with today. So whatever you need for the particular problem here, and oftentimes in engineering context, you need the function to be bounded in some sort of specific way, so the system that you're studying stays under control. But the basic picture is this. I give you a couple of points, lambda 1, z1, and lambda 2, z2, and I say, find me a function that goes through the points. Yep.
So this is not interpolation in the sense like you have like 2 points and you linearly interpolate.
So linear interpolation is a family of, it's one of the words you can put in here if you want to describe like how to do interpolation. Of course, the problem is linear interpolation is only possible if the points are collinear. And so usually when you're doing linear interpolation, you're actually saying linear interpolation in the sense of a best fit line, like from least squares, which is kind of like not really interpolation in a classical sense. Yep.
So what's the, you gave us 2 points. If you're asking for anything that's not a line, there's going to be like
Yes,
sequence.
which is a good observation.
Which one is the one we want?
Ah, so it depends on it. It depends. It depends. It depends on what you're after. So in this context, you're right. There's a unique line that passes through those 2 points, right? There's one line that will pass through those points. So if you look at this and you think, okay, what if I demand a polynomial just to make my world easier? What if in this problem I demand a polynomial solution? Well, from a degree 1 standpoint, there is a single function that goes through here. Let's see. So there's one sort of degree 1 function. That's a line, I promise. So there's a degree 1 function that goes through these things, and it's unique, right? 2 points uniquely determine a line, but there's a whole crap load of parabolas that go through these things. If, any sort of, you can imagine like sort of put the vertex, find the line between them, put the vertex and the midpoint of the line between them, and then just adjust how steep the parabola is, right? So you have this entire family of interpolating functions. So the functions that do this, if f of z interpolates the data, f of z is called, I guess we say f of lambda is called an interpolating function. If it does this. So the observation here is, yeah, there's a unique degree 1, but there's an infinite number of degree 2s, and there's even more, degree 3s that do it, right? So cubics, like quartics, you can do whatever you want. If you loosen your structure to be non-polynomial, the problem's even worse, because the number of continuous functions that go through those 2 points is absurd. Weierstrass functions go through it, so not even differentiable functions. All the exponentials can be set up to do this. All the logarithms can be set up to do this. Sines and cosines can be set up to do this. So oftentimes when we're doing these problems, it's good to be aware of the fact that the answer to these questions is highly non-unique. Okay. Sometimes. With additional restrictions, we can make the solutions unique sometimes. Okay. So normally when you're faced with an interpolation problem, let's do the 3-point problem, because this is the sort of classic one that you guys would have seen probably around the time, maybe in pre-calculus is where you see this problem the first time. I give you 3 points. I give you A1, B1, and A2, B2, and A3, B3. I give you 3 points that are not collinear. And I ask you to find the parabola that passes through those 3 points. This is a problem that should at least ring bells, right? You've done this a bunch. In fact, you learn it again in linear algebra after you learn how to do matrix solutions to things. So, when you're faced with an interpolation problem, basically the only 2 hopes that you have are elbow grease or a lucky guess. So the elbow grease solution to this thing is to say, well, maybe a parabola does it. And so you write down the system of equations that says, so the big question becomes, how do you find an interpolating function? How do you find an interpolating function? And this is actually where the idea of using polynomials turns out to be useful, because with polynomials, you just have a finite number of coefficients to deal with, right? If it's a polynomial, you've got some linear system. This is sort of where this subject is born. So in this particular problem, if you want a polynomial solution, you might guess that because there's 3 points that you can find a parabola that uniquely determines them. And so you write down the system of equations and say, oh, well, it must be the case that f of lambda is equal to c naught plus c1x plus c2x squared. And we're going to find c naught, c1, and c2. And don't worry, I'm not actually going to solve the system. I'm just going to write down what it would look like, right? So, so you say, there's your guess. What was the word we came up for guess last time? Ansatz. There we go. Pretty good guess. So you write down, okay, well, the target data should be equal to these unknown coefficients plus times my input data, c2, a1 squared, and b2 should be c0 plus c1, a2 plus c2 2 squared and b3 should be equal to c naught c1 a3 plus c2 a3 squared. And this is where you hit the elbow grease portion of the problem, right? Because now you get a system of linear equations and the unknowns c naught, c1, and c2. The idea here is that these are given and known, and the unknowns here are the coefficients of your interpolating function, right? So oftentimes, in a setting like this, interpolation problems turn into giant linear systems, right? Particularly when you're working with polynomials. So this is sort of the elbow grease version. Yep.
You always guaranteed to have a solution.
If they're non-collinear, yeah, there will be a unique. So 3 non-collinear points uniquely determine a parabola. Now, if I ask for a 4th degree polynomial, there will be an extra degree of freedom in the answers, and that's where the infinite family will come from, right? So again, we have the idea that with extra conditions, we can get uniqueness, and if we loosen those, we aren't guaranteed to have functions or the answers be unique. Okay, what if instead of wanting to spend our lives doing linear algebra without knowing what matrices are, like you did when you learned this for the first time? Remember all those Gaussian eliminations, which are big stacks of combining equations together? This is fresh in my mind because I tutored this stuff for like 6 years. So it's permanently glued in there. There might be a better way to do this. And this is the approach that the mathematicians of the 1700s took, which maybe we can just construct the solution. And so there's an approach called Lagrange interpolation. Which is really, this is not the ansatz approach. This is, I'm just going to grind it out and assume there's a polynomial and solve some giant linear system. The Lagrange interpolation approach is the clever approach. We're going to build the object. We're going to build the object that we want to make this happen. Some of you may have seen Lagrange interpolation before. It's like standard technique. It is like the standard technique for polynomial interpolation. It's also not very good because Lagrange polynomials aren't as good as, the Chebyshev polynomials, for example. But I'll leave that to the applied people. Okay, so what Lagrange interpolation says is, maybe if we're careful about the way that we set this thing up, we can just construct the function directly and not solve for anything. So, based on the data that we're given here, can you tell me a function that is equal to 1 when I plug a1 into it, and 0 if I plug in a2 and a3? That's question 1. Can I find, so we'll call this function f of little a1. Can you find f of little a1 that has this property? F at a1 is equal to 1, and f a1 at a2 is equal to f a1 at a3, which is 0. Can you find me a function that turns a1 into 1 and the other 2 points into nothing? Just a polynomial. I want just remember, this is Lagrange, this is polynomial interpolation, so it's a polynomial, right? The most basic function we can think of that does this. And the answer is you just write down some linear terms, right? It would probably have the term x minus a2 in it, so that when you put in a2 would disappear. And it would probably have x minus a3 in it, so that when you plug in a3 will disappear, right? And then, if you took this expression and you plug a1 into it, there'd be some sort of value. But I want the value to be 1, so I'm going to cancel out what would happen if I evaluated this thing at a1. This thing, if you put in a1, you'd get this would cancel with that, and this would cancel with that, and you would get the value of 1. And if you put in a2, you get 0, and if you put in a3, you get 0. So this is a function f of x that has this property. It's equal to 1 at a1 and 0 at the other 2, and these are called interpolating nodes. So if you construct 3 of these things that have the same property, but now maybe they're 1 at a2 and a different one that's 1 at a3, you can just chain them together into what's called the Lagrange polynomial, or Lagrange interpolating polynomial. So the Lagrange interpolating polynomial, so this is not an elbow-grease method. This is a observe the structure of the problem and pull some sort of information out of the structure to say, well, I can do that. I can just build it. I don't need to calculate anything. I've got a standard form that says the function that should do this is f of x is equal to x minus a2, x minus a3, over a1 minus a2, a1 minus a3. Okay, that does the first part. This turns a1 into 1, plus, don't worry, we're going to adjust it in a second, x minus a1, x minus a3 over a2 minus a1, a2 minus a3. That's the one that sends a2 to 1. X minus a1, x minus a2, a3 minus a1, a3 minus a2. This one will send a1 and a2 to 0 and a3 to 1. That's almost what I want, because I want this thing to spit out b1 when I put a1 into it. So how do I have to adjust it? How about I just stick the b1 right here, because the whole point of having this be equal to 1 is that it's very easy to make the modification that makes it spit out b1 at a1, b2, b3. So this idea, which is actually not due to Lagrange, I don't know why they named it after him. Like many things in mathematics, it's not named after the person who invented it. This idea is that this can be constructed for any set of points. And this approach also gives you, there's a theorem actually that says this is the unique polynomial of lowest degree that does this. So it's pretty powerful. Of course, the fact it's unique is awesome. These things also have terrible behavior. These polynomials are kind of trashy. They are. They go to infinity. Polynomials run away to infinity. That's terrible. Having things that fly away to infinity at the ends is awful in a lot of contexts. But at least whatever comes out of this is guaranteed to be in this case, the unique parabola that goes through it. Okay? So again, faced with an interpolation problem, you got elbow grease, or you have some sort of clever observation about how you structure a function. So let's level up the interpolation problem that we're going to be working with. Okay, are there questions about this? This idea here about Lagrange interpolation is the basis of a whole regime of approximation theory. There's books about this. This is not our subject. What I'm trying to lay out here is the basics of an interpolation problem says you're given points. Probably you have to make some sort of clever guess about where the function comes from, and then you want to probe the behavior of the things that comes out the other side. Yep.
So obviously this will work for any given polynomial, given you have the what's the number of points. Does it work for any other functions? Or is there a similar method that works for any other functions?
So you mean like polynomial? I mean, there's all kinds of interpolation regimes. Usually what you do is you want to restrict yourself to, so rational functions end up more, actually, so if you take Lagrange interpolation and you restrict your points to the upper half plane and you conformally map the entire thing to the unit disk, you get what's called the Neven-Linapic interpolation problem, which is harder because now you don't want a polynomial. You want to say, suppose I put the extra condition on, I would like it to be the case not only that I have a function that goes through these 3 points, but let's have it be a complex function, and let's have it take the upper half plane to itself. So that's a boundedness condition, right? So I want, if the imaginary parts of the inputs are all positive, I want the imaginary parts of the outputs also to be positive. That's actually sort of where you enter the realm of complex function theory. And then rational functions turn out to be necessary to do that as well. Yep?
So, funny enough, we actually in 451 learned this yesterday. But I was.
I'm not going any further than this, but okay.
That's okay.
All right.
It was explained to us that the reason why it's a unique polynomial is because it forms a basis of the polynomial vector space, subspace of degree, whatever it is.
Sure, yeah.
But obviously, we're going to work with complex numbers. So would you need an extra term each in order to...
The polynomials continue to be a basis in complex setting as well.
Even though a complex number is like 2 real numbers?
Yeah, but I mean, so the thing is that, that's called the Weierstrass approximation theorem that says that continuous functions can be approximated by polynomials.
Right.
A version of that holds in complex analysis. Analytic functions can be approximated with polynomials as well.
Okay.
Yeah, so that's ultimately what's going on in the background, is that you have that. Polynomials still form a basis of complex function spaces.
But you don't need, because you're over C, you don't need extra polynomials.
No, because the coefficients are also complex, right? Your
Okay.
polynomials are also complex and can be stretched in different ways
Gotcha.
because you're not trapped with real coefficients.
Gotcha, okay.
Okay, so let's ask a more interesting interpolation question, and one that mathematicians spend a long time thinking about, which is I'm going to give you a different set to interpolate. So think about this set. I'm going to draw, I should put the x-axis way down here. Okay, so I'm going to start drawing some points. 0, 1, and I'm going to put 1, 1, and then a 2. We're going to have a value of 2, and then a 3. Let's see, 1, 2, 3, 4, 5, 6. This would be 6. And then 4, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. All right, now, what are those, by the way? 2, 2, 3, 6. Up there is 4, 24. And suppose I just keep that pattern going forever, right? I want all the dots. I want that pattern to continue. Really, secretly write down as the factorials, right? So this is the function that, like, the other name of these points that's probably more familiar to you is 0, 0 factorial, 1, 1 factorial, 2, 2 factorial, 3, 3 factorial, 4, 4 factorial. And the question becomes, find me a function, a continuous function, that interpolates those points. Question is, find a continuous function. Maybe we'll give it the name. Maybe we'll call it, well, maybe we won't call it gamma yet. Yeah, we won't get, I want to give it away yet. Maybe we'll call it, maybe we'll use this symbol. Yeah. We'll call it function little gamma, right? Let's find a continuous function little gamma that has the property that if I feed in n factorial pops out the other side. That would be an interpolating function for the factorials, right? But also I want it to be continuous everywhere else. Yep. Or you just, resting elbow, okay. Right? So I want it to interpolate, what the condition I'm asking here is that it interpolates the factorials. And also, I would very much like it to be continuous. Because otherwise, you could just send every other point to 0. Yep. You can do all kinds of things with it. How is this related to that?
Yeah, like if like this, will that have to occur?
So I actually don't know how the gamma function is. I mean, the factorial function can be distorted with various parameters to recover other sort of factorial-like constants at the integers. So I think once you start it, you can just start twisting it around and with like parameterizations, I think. I have to look at it. I haven't thought about that. Every context I've seen this in, the generalized factorials and the combinatorial, and this I've only seen, this is the way I've seen this approach from complex analysis. It's a good question. I'll take a look at it. Okay, so now elbow grease isn't going to do anything for you here, because there's an infinite number of points to interpolate, right? So it's an infinite interpolation problem. You have no hope of writing down a polynomial function that does this, unless. No, you got it. We can actually do it. The other way to do it is you do it like Euler did with the sine function, and you just start building infinite products. You can imagine to yourself, what if I had sort of infinite products where there were zeros all over the place and I could spit the factorials out in special places? So there is an infinite product approach to understanding this question, right? Which is more of the elbow greasy version. We're not going to do that, or at least not yet. We're going to do the clever guess version first. Because the clever guess version of a function that does this requires you remember nothing except integration by parts. So, as there, I will remind you how integration by parts works. Okay, so when these guys like so Euler and Laplace and Lagrange and Weierstrass were working out the basics of function transform theory, right? So, like, what is the Laplace transform? How is it defined? When you don't care what you don't have to tell me what it is. How is it defined? It's an integral, right? And there's an e to the x running around inside there. How's the Fourier transform defined? It's an integral. There's e to the x running around inside there. The Poisson integral that we wrote down earlier that took the boundary into the interior of the disk, also an integral, right? Like there's this relationship between a kernel and the outputs. So basically these guys were playing around with integrals of certain shapes, and what they discovered was the following. So this thing, like let's think about this for a second. That's an obvious integral. If you're playing around with the Laplace transform, and it's like 1720, 1730, this is an obvious integral to like have considered, right? This is a very obvious thing to have considered. So the question is, okay, how do we integrate this? And I'm going to have to remind you guys about all kinds of things from calculus 3, right? Where you do improper integration and integration by parts. All right, so let's actually do that real quick. Let's see if we can discover any nice properties this integral might have. Okay, since I'm a stickler for working with infinity in the correct way, at least in the... Now, we are going to pretend complex analysis doesn't exist for a minute, and we're going to evaluate this using improper Riemann integration instead. Because if the improper Riemann integral exists, it agrees with the sort of like Cauchy principal values. So we might as well do it in the way we know. So the limit as n goes to infinity from 0 to n, and God help you if you use infinity like a number. Don't do that. In the real analysis setting, don't do that. For me, in complex analysis, now I get to be schizophrenic now, because on the one hand, we use infinity like a number all the time. But don't do it here. T e to the minus t dt. Okay, integration by parts, to remind those of you that haven't thought about this in a while, is you select a piece that will disappear if you differentiate it, like, I don't know, t, and then a piece that you know how to integrate, and you take the derivative of this side, and you integrate the other side, v is equal to minus e to the minus t, and then the integration by parts formula says that the original integral, which is u dv, is equal to uv minus the integral of v du. Is that ultraviolet? Yeah. So you get the limit as n goes to infinity. Don't worry, we're gonna wave our hands at this right now. I'm gonna write a line down, and we're just absolutely gonna wave our hands at it. So the limit as n goes to infinity of, let's see, we're gonna get a minus t e to the minus t from u and v. And then I have to do v du, which is going to get us the integral from 0 to n of e to the minus t dt. Well, there was a negative here, so it's minus minus, which gets you a plus. Okay, so here's where the hand waving starts. What's that equal to? 0. Boom. What's that equal to? That's a minus, not an I. Can't be 0, because you're putting 0 into an exponential. So 1. That's what comes out of that. I leave it to you to do that calculation, right? So if you do this, 1 comes out, okay? Let's try, what if, in the course of calculating your Laplace transforms, you said to yourself, man, I sure do a lot of this, right? 0 to n, the limit as n goes to infinity. What if you put a 2 up here instead? T squared e to the minus t dt. So now, u is going to be equal to t squared, du is going to be equal to 2t dt, dv is going to be e to the minus t dt, and v is going to be minus e to the minus t, and you're going to end up with a limit as n goes to infinity of, okay, so minus t squared e to the minus t from 0 to n plus the integral from 0 to n of 2te to the minus t dt. Oh, I know this integral already, so let's put the 2 out front. I know what this one is, because we calculated it over here. Right? And this is this integral. What was that integral equal to? 1. Oh, okay. So this is 2 times 1. So, we speculate then that the power of t that we throw up here is somehow influencing what's going on with the outputs that come out of this thing, right? That there's a relationship between the power of t and the outputs of this integral. And the pattern that you get here, because integration by parts is always going to be taking a derivative, if you put a t cubed up here, a 3 will drop out. And if you put a 4 will drop out. But there's this inductive thing going on where the value of the next integral will contain the value of the previous one inside of it. And so it turns out to be the case that we can make the following definition. Gamma of n, so now we're using actual big gamma here. This is the actual definition of the gamma function. Gamma of n is the integral from 0 to infinity of t to the n minus 1 e to the minus t dt. Yep.
So a bunch of French dudes sat around and noticed that this spits out the factorial.
So if you actually go and look at the Laplace transform tables, the Laplace transform tables actually have that factorial behavior built into the table, right? So what they noticed was, well, if we stretch the integral so that we're evaluating, you know, if we evaluate it slightly differently, we could just capture the factorials themselves, right? There are these constant factorial terms coming out. So it comes, you know, so they're very interested in studying physical systems and doing these sort of transforms, and they just picked up the fact that you could, how do you even prove that that works when you're taking the Laplace transform of, say, t to the n? You do it inductively, and the factorial shows up there, and one of them was like, oh shit, look, I could make the factorials this way instead of doing a transform. We could make the factorials. Yep. It's just convention. Just convention. It's basically so that I can start the domain of this thing at, I want to be able to have, there's going to be an issue at 0 that we want to avoid, right? That's really, that's kind of what we're after here.
So if you plug in 2, you're going to get 1.
1 factorial, yeah. Yeah, so, okay, yes. With the argument that we just made, gamma of 2 is 1 factorial, and gamma of 3 is 2 factorial, and gamma of 1 is 0 factorial. Right? We want to stay away from, it's just a way of staying away from 0 as an object of evaluation. This is just convention. You didn't need to set it up this way, but you did.
Are we only allowed to evaluate that at the integers? Is that why we're using it?
Good question. Because I've built this function now that produces the factorials. How do I know I can put any other number into it? Because this is actually where the big complex analysis move happens. Now I've got this integral, and it sure looks like it does the factorials. You can prove that this has the factorials. This has a bunch of nice properties that will, you know. Let me write down some properties first, including the most important property, which will answer the question that you're asking. So if I define, so the first thing is gamma of n is equal to n minus 1 factorial, which is really saying that gamma of n plus 1 is equal to n plus 1 times gamma of, n gamma of n. Because that's n minus 1 factorial, and n times n minus 1 factorial is n factorial, right? Okay, so these are as basic properties. You may, if you've seen the gamma function before in other contexts, this is actually sort of the combinatorial thing that shows up when you're doing like Pascal's triangle and various sort of combinatorial computations involving factorials. Okay, so the question is, why on earth should I be allowed to put other numbers into this thing? First observation is, then this is where like I want you to put on your, just for a second, your advanced, I've been doing calculus a long time and I can guess if integrals are going to converge or not hat. I got this integral and it's improper, right? It's totally okay at 0 because as long as you know just the thing about t you got to be careful of here, right? But what is e to the issue here is it going to be at infinity? What happens at infinity to this thing? If e to the minus t goes to infinity pretty damn quick, right? And if you have yeah, that's the basic idea. Is this exponential crushes t, any power of t, crushes it. So you have this sort of order of growth thing happening in the interior of this integral at infinity, right? Okay. And because you're evaluating at 0, I mean, as long as you're careful about the way that you set up the values of n that you plug in here, you're not going to have any sort of dividing by 0 problems. So the question then becomes, can I put other values of x into that? Will it still converge? What if I took the function and I said, what if I just put another real number? Let's let x be bigger than or equal to 1, just be some real number instead. And one of the first questions you ask is, would it make sense to calculate gamma of x where now x is not an integer anymore? So if x is not an integer, then you end up with the integral from 0 to infinity of t to the x minus 1 e to the minus t dt. Is there anything stopping you from computing the this integral? Just from like an order of growth argument? No, right? I mean, this exponential, as long as x is bigger than 1, you're not going to be dividing by 0, so there won't be a problem in the domain there. And as long as e to the minus t is going to crush any polynomial at infinity. Yep.
How would you actually integrate that, though?
Good question. Numerically.
Okay.
So the fact that this converges is a consequence of sort of a bunch of uniform convergence theorems about integrals.
Sure.
Right? So it's not a trivial thing to show that integrals like this actually converge. Right? You can use something like turn it into an infinite sum and show that the infinite sum converges uniformly, which forces the integral to converge uniformly.
Couldn't you, speaking to an analyst here, couldn't you just make an argument that you could bound it above by the highest integer, like to the power of the highest integer, or the integer that bounds x above, x1 above, and then like the integral would converge?
Sure.
And that's not that hard, right?
Well, I mean, no, but it means that like you're switching limits and integrals when you do that and doing s. Essentially, Fabini's theorem is going to be running around in the background here.
Oh, okay.
Right. So I don't want to get into the technical details of it because there's a bunch of people in here that haven't taken 412, and when I say Fabini's theorem, they're going, "Oh my God, we're not actually going to talk about that, are we?" So
Sure.
that's the. Yeah. So this will converge. This converges by analysis. But you should believe it, though, because e to the minus t goes to 0 pretty damn... If you actually plotted this thing, it crushes to 0 pretty damn quick. No matter how fast your exponential, your polynomial is growing, e to the minus t just smashes it to death. Okay. So that's the first thing. Yes, you can plug in the numbers between n. So there you go. That's your real valued polynomial interpolate. Of course, any sort of complex analysis worth their salt says, hey, look, you've got this really nice uniformly convergent thing sitting on the real line. We should just put complex numbers into it. Okay. So gamma of z is the integral from 0 to infinity of t to the z minus 1 e to the minus t dt. Any guesses as to where so I'm going to draw you what the convergence picture looks like in the real numbers. So in the real numbers, the convergence picture looks like this. Oh, sorry, real numbers. As long as you are here, everything is cool. Right? That definition of the function converges there on that strip. What is the natural domain? This is just a guess on your guys' part. What do you think you would need to have happen in order for this thing to continue to converge if you put a complex number into it? Well-
X don't have to be much of a real part.
Well, let's see. That's a good idea. Let's actually put gamma of x plus iy. So let's actually put the complex number in and see what this does to the integral. So gamma of x plus iy, and then we'll wave our hands furiously at it. T to the z minus 1, sorry, x plus iy minus 1 e to the minus t dt. This should remind you of the extension theorem, right? We have this function defined in the real line, and we're rolling the function off the real line because it was sort of this very nicely behaved function on the line. It's differentiable because it's defined in terms of an integral, so we should expect that it has like a way we can just plug complex numbers into it. So if you do that, if you put x plus iy in here, you get this. The integral from 0 to infinity of t to the x minus 1, where x is real, times t to the iy times e to the minus t dt. And just from the standpoint of analyzing what's happening in this picture, you should be able to figure out what the condition is. What does t to the iy do as y runs away to infinity? It just spins, right? It's like just this spinning object, right? It's like flying around. You're just changing the argument here, right? You're whipping around some circle. So this thing is rotating like mad as y goes to infinity, but the rest of it looks like the real integral, right? You have this exponential that's going to 0, and this t to the x minus 1, where x was real, that we already said was a convergent integral. So the imaginary part of that complex number only dictates how quickly the function is rotating as it goes to infinity. So this is a rotational element. It doesn't contribute to the size of the integral. This is controlled in growth by e to the minus t, so as long as the x satisfied the same condition that it did over there, everything's okay. So it turns out to be the case that this function converges as long as the real part of z is positive. Yep.
Is the argument for the spinning because, like...
Well, y is a real number, right? So,
right.
Yeah.
But how do you... We're used to thinking about polar forms of complex numbers being base e.
Yeah.
Is the argument like you can always write to the power of something as like y to the power of something times something else to the power of something?
Well, I mean, t is a real... Remember, t is strictly real here, right?
Right.
So if you take t and you write it in its polar form, even if like you let t not be complex, right? You take some real t and you raise it to an imaginary power. I'll let you think about what's 2 to the I pi over 2.
I mean, my first thought would just be to like rewrite it as e to the power of whatever and try and like see where it goes. Oh, okay.
Yep.
Why is the real part only positive now and not just greater than or equal to 1?
Because the way that we set this up was that it was okay to put. Actually, how did we set this up originally? Oh, it turns out to be the case that as long as that's a good question. It should be greater than or equal to 1, right? The way I set this up. Did I just make some sort of dumb? No, this thing is actually, okay, I should be careful here. This should have been 0. That this is the subtlety in the argument, is that you can actually take this function all the way up to 0, right? And so this is equal to, yeah, this is where the analysis comes in, because there's this bridge in the middle. Bigger than 1, it's obvious. Between 0 and 1, there's a little bit of work to do, okay? So that's the condition I want to carry over here. All right, now I want you guys to see if you can make the leap about what we do with this function. So the first thing is that the gamma function turns out for some reason, because it, the first reason is because it actually produces the factorials, any formula from applied math or physics or pure math involving factorials that's defined on the integers, if you extend it off the integers, usually it involves gamma functions as recording what happens to the factorial part of what it was that you were doing. So that shows up even in sort of the study of Laplace transforms. We only give you Laplace transforms for integer values of t, because nobody wants to take the time to show you what the gamma function is, and the formulas are nastier with the gamma function inside of them. Right? Maybe not for you. Because I'm sure you've seen them before. You've not seen them, okay. Yeah. The other thing is that you want to do is, now that you've got this beautiful function, how can we, could we like put more numbers into it? So right now we're allowed to do this. I know I can't do it here at 0. Is there anything else I could, because that's to do with the sort of p-series thing, right? What else, what could I do with it? And I'm going to give you one more tool because I haven't asked you a fair question.
So if you use a conformal map to map the reason you can do it to something else.
So, yes, although that's pretty atrocious when we actually look at what's going on here. Yes, that's one thing. You can actually take the gamma function, you can flop it around conformally. The other observation is that this equation right here that relates the fact that the behavior on integers extends to complex numbers as well. So there's a functional version of this equation that says if you trace through the argument using integration by parts, you get you don't get this sort of inductive stack back down to some starting point. But integration by parts will actually give you that gamma of z plus 1 is equal to z times gamma of z. This is called the functional equation. Okay, so right now this is what we know. We got this property, we've got this one. We know that it's really nicely behaved when we put in 1 and 2 and 3 and 4 and 5 and 6 and 7. You can make an argument from estimates that this definition extends all the way out here to the imaginary axis. Can you think of how we might use this to think about how the domain of this thing extends? So I'm going to leave that open for a second. There's something about this equation and this picture that interact with each other to tell you what the domain of this function actually should be. There's something this relation induces. Now, before we go on to that, I want to tell you that this is sort of our next idea here in the class. Is going to be the idea of what's called analytic continuation. And analytic continuation means extending the domain of analytic functions. This is important in a lot of contexts because it's like, oh, I've got a solution to some problem over here. I can broaden the set of situations I can apply that in. If I can take this if I can maximize the domain, I can apply the function in. Yep.
If you think about the complex numbers in polar form and you multiply it by a complex number by complex number, you get the rotation that puts you on the left side.
You do. That's more sophisticated than I'm looking for here. Yeah, okay. The fact that like I've got the what does z plus 1 do? Think about like I want you to think like the very first time you learned about, plugging shifts into functions. What is this? Z plus 1 is what? A right shift it's a left shift by 1 unit, right? So this gives you a way to define what's going on over here because you're saying, well, that's totally okay as long as the real part of z is positive, right? But that says that you could plug any z on this strip in here too, right? This little band right here, where z is equal to minus, where the real part of z is equal to -1, that chunk will also be okay because that chunk is defined in terms of the chunk that starts at 0.
And is that chunk okay on the real axis as well?
Yeah. But you can't do it at 0 because 0 wasn't defined. So there's a hole right here at -1. Oh, but now what? Now you can use the fact that you've stripped it out to -1 to go, oh, I'll just go one chunk more because since it's defined out to -1, this says it's actually defined out to -2. So you just kind of like chunk these strips onto the edge by saying, look, that lets me translate to the left as far as I want.
So it's defined everywhere except at...
Everywhere except 0 and the negative integers. This function is actually meromorphic.
But don't people take negative factorials that are integers?
You got to be really careful with what you mean by that.
What sort of, like, plug in -1 and
There's a
1?
different formalism for doing that.
What sort of holes are there? Can I take the limit of angle towards one of those holes?
You calculate
Does it
residues.
actually convert
There's
to
residues. This has a residue theory attached to it. You could calculate the residues at these singularities if you want to. If you want to.
So I could, so does the function actually, is it like removed from singularity, does it actually go?
It's not removable.
Okay.
It's not removable.
So it actually, as you approach that, your limit doesn't converge.
Well, yeah, they're poles, right? So they run away to infinity. So anyway, yeah, the idea here is that one way of extending a function when you have some sort of structural equation like this is to say, well, I had it defined here, and I've got an equation that forces it so I can do it here, but that one gets me this one, and that one gets me this one, and that gets this one. And so the gamma function extends to, you know, the entire complex plane except for the negative integers at 0. So then, that means if you were on YouTube and trying to make people scratch their heads about stuff, you might say, oh, -2 plus 3i factorial is equal to something. But really what you would mean when you said that would be, oh, you take gamma of z, which is equal to the integral from 0 to infinity of t to the z minus 1 e to the minus t dt, and then you use this shifting idea to define the function out here somewhere, and then you take this number and plug it into this expanded domain version of it. It's not really calculating a factorial. It's calculating the value of the gamma function here, right? So people are really sloppy with this and make controversial math videos. But anyway, so the big point of the gamma function is it reproduces the factorial, the factorial numbers at the positive integers. It's analytic on the right half plane, and it's meromorphic on the entire complex plane, which is a pretty nice interpolating function, right? Okay, now my question for you for next time is it the only function that reproduces the factorials? Because in the earlier problems we had non-unique interpolating functions. Is gamma function the unique function that produces the factorials, or are there more? Yep.
What does meromorphic mean?
Meromorphic means that it can be written that a meromorphic function is a function that has poles instead of essential singularities.
Okay.